So let's see. So now, till now we were actually doing relativity like in more formal aspects. Now what we'll do is we'll apply. So I've started recording, right? Yeah. Oh, I've also not started sharing. So now it has started to share. Okay, so you can see the screen, right?
Yes, sir.
Good. So what we'll do is now we'll apply relativity to, to radiation. Okay, and so the idea is like, we did this Doppler formula already, but that was done in particles rest frame, right? When we considered this accelerating charge, we thought that it was at rest, but it was accelerating, so it was instantaneously at rest. Now we'll have situation in which we have particles which are moving, and not only moving, they are moving relativistically. So let's see. So we have this, always remember this geometry that we have. Oops, just a sec. I don't want such a thick line. Okay, so right. So we have these two frames, right? So this is the lab frame, and this is the frame which is moving with velocity v, right, relative to the lab frame, which we call S prime. Okay, and this is the, for our purposes, this is the particle rest frame. Okay, so we are considering particles which are radiating. So, the big picture game plan is that we have already looked at things like, Larmor formula, etc., which were done in this frame, particle rest frame. But, in general, we are interested in the lab frame. So we will we'll use expressions in frame S prime and transform them to frame S. Okay, so that's the program, and that's where these relativistic transformations, Lorenz transformations, are going to be useful. Okay, so don't forget this picture. So there are, for example, you have a so for example, you have like a particle oscillating, it's accelerating and oscillating. So this is the frame that we already considered, right? This is a particle rest frame. Instantaneously particle is at rest, but it is accelerating. So this is stuff in S prime, but we want to go from here to frame S. Okay, let's get started. Okay, so the first thing is power radiated. Power radiated is Lorenz invariant, or Li. This is what I'm going to use. So basically what is meant by Lorenz invariant? What it means is that it's a scalar. So if I measure power, total power radiated in frame S prime or in frame S or any other frame which is moving relative to frame S or S prime at a constant velocity, I'll measure the same power. Okay, what is power? Power is energy radiated per unit time. So let's see how we can motivate this, that power radiated is a Lorenz invariant. Okay, so let me just write this. So dt prime. So this is the so what is power radiated? Power radiated is d. Right. So this is this is energy. I'm using W for energy just to be consistent. So energy radiated in photons. Okay, and this is the time. So this is the time in this interval time delta t. So this is power P as measured in frame S, and P prime is the power as measured in frame S prime. It's just dw prime by dt prime, right? We know that S prime is the particle rest frame, so don't forget this. So what do we know about dt, the relation between dt prime and dt? Right, we know that right, so this is particle rest frame, so the time measured in frame S will be longer because of time dilation. Okay, so what do we have? We have dt is equal to gamma dt prime. This is nothing but time dilation. Right, so here the events are happening in at the same location in frame S prime. So for example, emission happening in S prime at this instant of time, okay, will look the same two events which are happening at the same location in S prime will look will be observed to have a longer time lag between them. Okay, so we are actually calculating power, so this is the denominator for that expression. Okay, what about energy? How does this energy? So this energy is the spread in the change in energy in time dt prime. So what is this? We know that energy momentum, right, is a 4 vector, right, even for photons. So this here we are talking about photons, right? This is what h nu and h cross k, yeah. So this is a 4 vector. So this satisfies Lorenz transformation. So this is equal to gamma dw prime plus c beta dot delta p prime. Okay, so basically we are considering right, so we are considering photons which have a spread in momentum. So how do I say this? Just a sec. So this beta is this, V is equal to beta C. Right, so in particle rest frame, right, we know that if particle is accelerating in this direction, this is A prime, so this is particle rest frame, right? The radiation, for example, dipole radiation is symmetric respect to any direction, right? So for example, this direction, you have equal power going in forward and the backward direction, and this is true for all directions. So right, so if we are in the particle rest frame, the spread in right, so how do I say this? Okay, so so this is how we say it. So the energy that's right, so this energy, actually this energy is energy radiated in photons. This is also equal to energy lost by particles, right? Because whatever energy particles lose comes out in photons. So we can actually think of this as energy change in energy for the particles, right? So this here particles, this is the change in energy in particle rest frame. This is in the lab frame. And we can then think of this is change in momentum of particles in their rest frame. Okay, but you see, in the rest frame of the particle, a photon is equally likely to come out in this direction and in this opposite direction, right? So the particle's momentum does not change. Particle's momentum doesn't change. What it means is that delta P prime in the particle's rest frame is actually zero, because we are considering symmetric emission in particles rest frame, and we know this is true for dipole radiation and for other radiations as well. So this is actually zero. So what do we get? We get the change in energy of the particles in the lab frame is equal to gamma times change in the energy of the particles in the particle rest frame. Okay, and this is actually related to whatever particle has lost has come out in photons. So you see from this equation and this equation, if we take the ratio, we get dW dt is equal to dW prime by dt prime, right? So or power is equal to total power emitted as measured in the lab frame is the same as total power emitted as measured in the particle rest frame. So power radiated is a Lorenz invariant, right? So what it means is that if you integrate over all solid angles, right, then you measure same power irrespective of the frame that you are measuring it in. Very, very powerful result actually. So you appreciate how we derived it. We actually did not look at the change in energy of photons. We said that the change of energy in photons is equal and opposite to the change in energy of particles. And then we, by the symmetry of emission of photons, we said that the particle's momentum on average does not change. So this is set to zero and we get this relation. And then we get this power radiated is a Lorenz invariant. Okay. So what it means is that we know the expression for P prime. We know the expression for P prime. So what is frame P prime? Right. So you have, say, some electron or something accelerating. Okay. It's accelerating. So we are looking at the particle rest frame. It's accelerating, but at this time, its velocity is actually zero. This is the definition of particle rest frame, that the particle is instantaneously at rest. Okay, and when we derived this dipole formula, we actually considered only acceleration. We did not consider any velocities. We set v equal to zero. So our expression, if you recall, was 2/3 e squared a prime squared by c cube. Right. We know that electric charge is a Lorenz invariant. It's a scalar, and a prime is the acceleration measured in the particle rest frame. So this is this transformation is done at that particular instance to a particular frame where particle is at rest. So you can be at rest, but your acceleration need not be zero. So give me an example of a case where something is at rest but it's accelerating. Any simple example, right? We are all familiar with a lot of such examples. Anyone?
During free fall, when an object reaches the maximum height, it will be at rest momentarily, and
Absolutely. So this is a ball thrown up and coming down in a parabola. At this point, at its maximum height, its velocity is 0, but of course its acceleration is, it's at all points is g acting towards the ground. So this is an example, right? So we can always consider this frame in which instantaneously the particle is at rest. So even here we can instantaneously go to a frame which has a velocity which is in this direction for that particular time, right? We'll have to change this frame as we are at different places on the trajectory. Okay, good. Right, so this is the radiation power. Okay, and we said that this is a Lorenz invariant. That is, it's the same as it's the same. The left-hand side is the same, whether we measure it in frame S or S prime. That means A prime, right? The acceleration measured in the particle rest frame also must be a Lorenz invariant. We should be able to write this in a form which is manifestly a scalar, right? So we say or something which is Lorenz invariant is basically a Lorenz scalar. It transforms like a scalar, right? What is a Lorenz scalar? Like ds square is a scalar, right? And e squared minus p squared is equal to m squared c4 is a scalar. So basically whatever that remains the same in the two Lorenz frames is a Lorenz scalar. So we should be able to write this in a Lorenz invariant form, which is manifestly shows that this is a Lorenz scalar. So let's see. We know we have this 4 velocity, right? And how is this 4 velocity defined? This is nothing but gamma u c gamma u u, right? So we can have a particle moving with velocity u. We can define a 4 velocity for it, and you can actually see that it satisfies this condition that minus gamma u squared c squared. So right, so u mu u mu, right? This is like a dot product in the 4 space is equal to plus gamma u squared, right? And this is nothing but minus gamma u squared c squared minus u squared, which is nothing but minus gamma u squared c squared 1 minus u squared by c squared, which is nothing but 1 by gamma u squared. So this is equal to minus c squared, which is Lorenz invariant because c is a universal constant. So this is basically this is 4 velocity and this is a Lorenz invariant. Okay, or a Lorenz scalar. We can also define 4 acceleration, right? So this was nothing but this was actually dx by d tau, right? Where d tau is the small proper time, which is a Lorenz invariant. So if x is a right, you call right x alpha is equal to ct and x, the normal position vector. So this is a Lorenz, vector. X is a Lorenz vector, but d tau is a Lorenz scalar. So the ratio of a vector to a scalar is a vector. So similarly, this is equal to du by d tau. This is called, this is 4 acceleration. This is nothing but d2x by d tau squared. Okay. Right, so let's see. So, the program is to actually write this in a Lorenz invariant form, A prime in a Lorenz invariant form. Let me create a little more space. Okay. So let's look at A dot U, the dot product of 4 acceleration and 4 velocity. What is this? This is nothing but du by d tau. That's for acceleration dot u. What is that? That is nothing but d by d tau of u dot u, half of that, right? I'm just sort of if I just expand it by a dot b, taking the this is clear, right? How do you go from this to this? And this is what? D by d tau of u dot u by 2 is nothing but d by d tau of minus c squared by 2, which of course is 0 because c is a constant. So what it means is that A is always orthogonal to u in in this 4 space, not in 3D space, in this xt space, right? Okay, so now, so what this means is that A dot u as measured in particle, in some frame S is the same as A prime dot u prime, so the right hand side is measured in the particle rest frame, right? In particle rest frame, what is u prime? U prime, this is equal to this 4 vector u prime is equal to gamma u is 1, so this is c u, so this is basically this, right? U prime is this, A prime is equal to right, so this is the acceleration measured in the instantaneous rest frame. So what do we get? Just a sec. So A prime squared, this is what we need here basically, right, is equal to A0 prime A0 prime plus AK prime AK prime. Right, I'm just sort of so I'm just sort of writing it in a 4 vector form. Let me see.
So one should be minus, no? Means.
Yes, this one is minus. Right. So let's see. Right. So I'm trying to write what is A prime, the 4 vector, and what I'm writing it as is 0, comma A prime. Now, why is this 0? So this is actually the argument, right? So what is this? This is d by d tau of gamma u c, right? So this one, this component is that, and c is a constant, so c d by d tau of gamma u. But recall, we are in the particle rest frame, so gamma u which is equal to 1 minus v square u squared by c squared minus a half, right? So u is actually almost 0, right, for this particular time. So this is like 1 plus u squared by 2c squared, right, which is almost like 1 to linear order in u. So gamma u is that. So to linear order in u, a prime is actually 0, a prime 0. So this is actually 0, and a prime square, the 4 vector square, is equal to that, and that is a Lorenz invariant. So basically this is equal to this dot this, which is a, you know, a dot product of 2 4 vectors, right? So this is a Lorenz invariant. So this is the manifestly, if we replace this, right, the rest frame acceleration by a dot a, we get the so we have this is equal to 2/3 e squared by c cube a dot a. So this is the Lorenz invariant or manifestly scalar form of power radiated. Okay. So now you can actually calculate this a dot a in whatever frame you like, but this was actually motivated from the rest frame expression for Larmor power. Okay, now how do we write this? You know, suppose you're like doing an experiment and measuring acceleration in this frame. So, you know, this is the lab frame and you're doing your experiment here, you know, your particles accelerating in this frame. So you are able to measure acceleration in this frame. So acceleration is what? Is equal to d2x dt squared as measured in this frame, right? So from an experimental point of view, this is easiest to measure, and we want to be able to write our power formula in terms of a rather than a prime. How do we do that? Let's see. If you recall our velocity transformation formula, right? We were using these Lorenz transformations, right? If you recall, there was x prime is equal to gamma x minus vt, y prime equals y, z prime equals z, and t prime equals gamma t minus vx by c squared, right? So what we did was velocity u was equal to dx by dt, and u prime is equal to the change in x prime by change in t prime, where x prime and t prime are the difference between the two, you know, between how much x changes in time t prime. So we did this, right? We obtained these velocity formulae, if you recall, that u x prime equals ux minus v. We are sort of taking a boost in the x direction, right, by 1 minus v ux by c squared, and u y prime equals uy by gamma 1 minus v ux by c squared, and you know the same expression was obtained for z. You remember this? Right? It's just like taking the ratios and using these definitions, right? Similarly, what we can actually do is you can do dux prime by dt prime, which is equal to ax prime, right? We can again do the same exercise of taking the derivative of this, which will give us how A transforms from one frame to other. So we so in fact this is one of the homework problems. Is this okay, where you have to actually, just like we connect u prime to u and v, we have to connect a prime to a and v. Okay, so what we get is so right, and recall, so this is for a general velocity difference v, right? So you know there is v and there is u in this problem, right? So v is this velocity difference between the two frames, right? This is moving with velocity v, this is the frame s prime, this is frame s. U is the velocity of a particle which is moving in this frame, right? So when you, so the question is, if you go to some general frame which is moving with velocity v, what will be the how will the components of the velocity u of the particle change, right? So but in this present problem we don't have a general velocity boost, right? This we are actually in the particle rest frame. So this v and this u are the same because we are considering a particle with velocity u. Okay, so so what do we get? So so our u and v are actually the same in that case. So what you get, so let me how do I do it? Right, if you do this exercise, you will get some formulae like A parallel prime is equal to you know, A parallel, you know, some functions of gamma, which is a function of u. There is no v in this case, right? Because you know we are only considering particle with velocity u in the lab frame. Function of gamma u, and what else? So you know this is just tedious. It's not hard to do. You'll get some function like this, but when we are looking at a particle rest frame, right, we can actually set we can set u right. So basically the situation is that you are in a frame in which particle is at rest. So basically this v is the particle velocity. So in that case you can actually show that let me just write down the expression and then just explain what I have written down. We can write A parallel prime is equal to gamma cube A parallel, and A perp prime is equal to gamma squared A perp. Okay, what have we written here? So right, so this is your acceleration A prime, right, in the particle rest frame. So this is measured in frame S prime. Okay, and the particle has an acceleration in this direction, but it can move. It will have a u as measured in the lab frame in this direction, right? Is it clear what I'm trying? So u prime is 0 by definition of the particle rest frame, but u as measured in the lab frame is in this direction, A prime is in this direction, and what we are actually concerned about is this. So we can actually this is your velocity. Oops. This is your velocity direction. So what we can actually do is you can write your A prime as A parallel U hat, A parallel prime, and this one is a perp prime, right? You can always decompose the acceleration into a vector along the direction of the particle and perpendicular to the direction of the particle. So if we do this exercise of how accelerations transform under Lorentz transformations, you will get this. When we plug in ux, when we plug in v is equal to u, and here gamma is equal to actually gamma u, because there is no other v here in this problem, and that's equal to 1 minus u squared by c squared to the minus a half. Okay, is it clear what I'm doing here? These are the Lorentz transformations of accelerations from lab frame. This is how the rest frame acceleration and the lab frame acceleration are related. Okay. So this is actually homework number 4.3 in Rybicki and Lightman. Okay, and in that problem, what you have to do is you have to plug in ux prime is equal to 0, right? That's the definition of the rest frame. In the rest frame, u prime is 0, and then you will get this expression. So what does it mean? What it means is that p, which is equal to p prime, is equal to 2 by 3 e squared by c cube a prime squared, right? What is a prime squared? Which is a parallel prime squared plus a perp prime squared. So this is the total acceleration, square sum of the acceleration along the direction of instantaneous velocity and perpendicular. And this is, when written in the lab frame measured acceleration, it's nothing but 2/3 e squared by c cube gamma to the power of 4 gamma squared a parallel squared plus a perp squared. Is this clear? I just substituted this in this formula. Right, you see how sensitively it depends on gamma, right? If you have a particle which is moving very, very fast, relativistic particles emit efficiently, right? Because of these factors of gammas, right? And if you also recall, right, in our electric field expression, there was like 1 by kappa cube. If you recall, E radiation had this 1 by kappa cube, which was 1 by 1 minus n hat dot beta, right? I mean, when beta goes to 1 and n hat is along the direction, right? Here we are actually looking at the directional dependence. Here we have integrated over all directions, but these high powers of gamma means that relativistic particles are very efficient emitters of radiation. Okay, so this is actually important, but you should also be aware how we sort of went through this whole derivation. First, we motivated that power is a Lorenz invariant, and that means that we can actually just use the same expression 2/3 e squared by c cube times a prime squared, and we can easily calculate a prime in terms of a, and that's what we did here. Any question on this? So this is about total distribution of power in all angles, on all solid angles. Now we will actually move to angular distribution of power, which is Okay, now we'll move on to angular distribution. I mean, this material is very important because here we are actually applying relativity to radiation, and this course is about radiation. So later on, when we do synchrotron emission, we will use some of these results. So try to follow the arguments. Okay, so that was all about the previous part was about total power. Now we are concerned about how much power goes in what direction. So we'll have emitted power and and received power. Okay, so this is the setup. Let me actually draw. Right, so we have this. So we have to worry about, in this particular case, we have to worry about the transformation of the solid angle, right? Because, so, let me just draw, say, the particle rest frame. This is frame S prime, right? So now you have some angle theta prime, and you are actually considering these photons which are distributed, in this small solid angle d omega prime, and right, so this is some, this is the direction of the velocity. So this is frame S, right? So this frame is actually moving with velocity. So this is moving with velocity u, which is the particle's instantaneous velocity. This is the lab frame, and in that theta prime is actually this angle theta prime goes to angle theta, and this solid angle goes to d omega. So the question is, how do thetas transform? So let's actually, this is, so we can actually take the velocities in the x direction without loss of generality. So we can choose our x-axis along the direction of velocity. Now, then you have the other angle, the azimuthal angle, right? If we consider so this is just a second, x, y, z. So this is your azimuthal angle, phi prime, right? So if this is the direction of motion of the particle, there is theta prime and phi prime, which get mapped to theta and phi, right? Is the geometry clear? So we can actually, so x, y, z. I mean, these are sort of like your spherical coordinates, except that x is like your z. Do you see what I'm trying to say? We have chosen x to be the direction of the velocity. I think the book also does that, but perhaps would have been better if x were chosen as z. But the idea is that these are theta and phi, your standard, spherical theta and phi. You get it? Hello?
Yes, sir.
Good. So how about theta? How do thetas transform, right? We know that, I mean, let me just write down phi prime. So phi prime equals phi. Let me show why. So what is phi prime? Phi prime is nothing but tan phi prime is equal to dz by dy. I mean, this is basically the angle between y-axis and the z-axis. So tan phi prime is that, and tan phi is equal to dz by dy. Right, we know from Lorenz transformations that the transverse directions are unaffected, right? dz prime is equal to dz and dy prime equals dy. So their ratios are also the same. So phi prime is equal to phi. Clear? The azimuthal angle, right? The angle in the plane perpendicular to the direction of velocity, which is x, that does not change. What about angle theta prime? Theta prime does change, and in fact we have actually talked about this angle theta prime in the aberration formula, if you recall. If you recall, we did this, right? We did this tan theta is equal to uy by ux, the velocity in the x direction and y direction, and tan theta prime is equal to uy prime by ux prime. I don't know, that's the angle theta. This is the direction of the particle, and theta is some, n hat, some angle in which you're considering the photons. N hat prime, this is n hat actually. Okay, and we actually derived this formula, if you recall, by using the velocity transformations. We actually derived that cos theta is equal to cos theta prime plus v by c, or u divided by 1 plus v by c cos theta, right? So here we are considering photons. We are considering photons along some omega hat, right? So we are actually considering that velocity. So we are considering photons. So basically for photons, this is really for photons, right? These thetas are really for photons measured in lab frame and in the particle rest frame. So this was the expression. Right. So for u, we are actually putting equal to, so u is equal to c is what we are actually putting, and that's how you got this formula, right? Here v is actually v here is actually the particle velocity. Okay, so this is the velocity of the particle. U, the particle of the velocity of photons, has been set to c. Formula that we derived a few classes ago. Okay, so what does it mean? So we can actually define mu equals cos theta, and mu prime is equal to cos theta prime, right? So mu is the standard variable that we use. So this means that mu equals mu prime plus beta divided by 1 plus beta mu. Sorry, this is theta prime. Right, so this is how theta and theta prime are transformed. Got it? This is from this aberration formula. For light. Okay. So there is also another way of looking at it. We can actually look at it from this. So dW, or the energy change, is equal to gamma dW prime plus V dPx prime. Right. So we are considering change in energy, spread in energy. This is spread in photon energy in lab frame. The same thing in particle rest frame. V is the particle velocity, Px prime is the photon momentum along the x direction in the particle rest frame. right? This is particle rest frame, not photon rest frame, right? So this is nothing but like the what do you call it? The Doppler, relativistic Doppler formula. So this is gamma dW times 1 plus beta mu prime, right? So this mu prime, so you know px is nothing but E by, you know, energy of a photon by c times cos theta, right? This is the momentum. This is E is the energy of the photon. So you know momentum is E by c for particles, but this is the x component. So you take cos theta prime actually, because this is written in the particle rest frame. So this is this dW prime, right? Clear? So this is how the energy in the lab frame and then the energy in the rest frame are actually related. Okay, so this is an important formula. This relates theta and theta prime, and we can actually write another, we can actually write, the inverse transform of this is just mu prime. When we do inverse transform, what do? We change beta to minus beta, right? And mu prime to mu. Got it? So this is the inverse formula for this. And we are actually, this is for angles theta. What about the solid angle, small solid angle d omega? For that, what is d omega? D omega is equal to d mu d phi, right? Sine theta d theta, right? D mu is sine theta d theta. So this is just d mu d phi. And d phi prime and d phi are the same. So this is, so d omega prime is equal to d mu prime d phi prime, which is nothing but d phi. So so we'll actually have to do, let's actually take the derivative of this. We can actually show from this that d mu is equal to d mu prime divided by gamma squared 1 plus beta mu prime squared. So this is how the differential, the change in mu or change in theta is related to, right? So this just comes from taking the derivative of this, right? And recalling that beta is equal to 1 minus, beta is just b by c, and gamma is 1 minus beta squared minus 1/2. Okay, so so let's see. Right, so this is the relation between the energy spread in the lab frame and the energy spread in the particle rest frame, right? So let's see. So dW by d omega is equal to gamma dW prime by d omega times 1 plus beta mu prime. So what we have to do is, these are lab quantities, but we have, the quantities that are easy to evaluate are the ones which are in the particle rest frame. But what we want, the answer that we want is in the lab frame. So we have to do these transformations. Okay, so this is, but we know that d omega is equal to d mu d phi. This is equal to d omega prime times gamma squared 1 plus beta mu prime squared. Is this clear? This one, the last equation that I wrote, I just substituted d mu equals d mu prime by gamma square 1 plus beta mu prime squared. And I use the fact that d mu prime d phi prime is equal to d omega prime. So this is nothing but gamma cube 1 plus beta mu prime cube, and this one and the squared from there, d omega prime by d dw prime by d omega. So this is how the spread in energy per unit solid angle transforms. So the previous slide was about transformation of total power. Now we are looking at the power along a given direction. How does that transform? Okay, and clearly this is not a Lorenz invariant because there are these factors floating around. Okay. What about power? This is just the energy spread within solid angle omega. So we have to divide this by some time. There are two choices for dt to divide this by. Right, one is dt equals gamma dt prime. This is the usual time interval measured in the lab frame. This is just Lorenz, what do you call it, time dilation, right? And in this, what you're saying is how much power, if we divide dw d omega by dt, what we mean is P emitted d omega is equal to energy per unit solid angle per unit time elapsed in the lab frame. Okay, so this is this is related to the emission or emission power or power emitted. Okay, the other choice is dTA, the time interval between the arrival of photons, and that is given by 1 gamma times 1 minus beta mu dt prime. If you recall, in our Doppler, in the discussion of Doppler shift, relativistic Doppler shift, right? We considered this case where particle is moving, and it's sort of, we are considering emission of photons along a particular direction, and we found that the arrival time, right, this arrival time is actually given by this. If dt prime is the time interval between, say, emission of pulses in the particle rest frame, if that is dt prime, then the arrival time is actually related to this by this, and this is also related to the Doppler formula, right? So instead of dividing by the time scale of emission in the particle in the lab frame, if you divide it by dTA, right, that would be dw by d omega dTA. We actually call that power, the radiated power by d omega. So here also we are actually, here and here in both cases we are measuring power in the lab frame. Here we are actually dividing by the time step between the emission of these photon pulses, or these photons. Here we are actually measuring the time step between the arrival or detection of these photons. So this is, we sort of denote it by radiation, by R. this by emission. And they are actually different. You can actually see that. So let's see if we make these two, and both choices have their uses. Here we are actually looking at how much power is received, right? You recall this is the photon chasing photon effect. Basically, if the particle is moving very close to the speed of light along the direction of emission, then the arrival time of the photons will be very, very short. Let's see. So now we will actually try to see how this and this transform from rest to the lab frame. Let's go down. Okay. Okay, so dPe by d omega is equal to dW d omega dt is equal to, we have that formula on top, right? So gamma cube 1 plus beta mu prime cube dW prime d omega prime. So we have to divide by dt, but dt is nothing but gamma dt prime, right? Lorenz time dilation. So that's nothing but gamma squared 1 plus beta mu prime cube dw prime by d omega prime dt prime, which is nothing but, actually let me erase this and okay, just write it as d e prime by d omega prime. So this is the emitted power along a direction omega prime. Emitted power along omega prime in particle rest frame. This is particle in photons emitted along omega prime. So these are concepts related to radiative transfer. We are sort of writing them in this language, right? In radiative transfer, we had energy per unit time, per unit solid angle, per unit area. So this is the same solid angle. Okay, so this is how this transforms, and we can actually write mu prime in terms of mu, the angle measured in the lab frame. How do we do that? So this is mu prime. So let me, these things are easy to do actually. Let me show another useful identity. Gamma times 1 plus beta mu prime is equal to 1 by gamma times 1 minus beta mu. This is another useful identity. All these can actually be obtained from the first expression, right? And the second expression. So if you just manipulate this a little bit, you'll get this. Okay. So using that, we actually get, so 1 plus beta mu prime is equal to 1 by gamma squared 1 minus beta mu. So this actually becomes 1 by gamma 4 1 minus beta mu cube dPe prime by d omega prime. So this is power measured along a solid angle omega hat in terms of the same thing in the particle rest frame. So you see there is a huge power of gamma and 1 minus beta mu, which is nothing but like kappa. If you recall the kappa factor when we're doing classical E&M, this is also something like this also appeared. Okay. What about the other one, the dPr by d omega? This is equal to I mean, again, what we have to do is dw by d omega dta. We have to now divide by this arrival time difference, and that is actually equal to, we can actually show that this is gamma 4 1 plus beta mu prime 4 dp prime by d omega prime. This is equal to 1 by gamma to the 4 1 minus beta mu to the 4 dp by d. Right, so this is how the radiated power, where this you divide by this arrival time, goes like. Okay. So we will actually a lot of time consider cases. Just a sec. Give me a second. So in a lot of cases, we will actually be considering particles moving relativistically. So beta is close to 1. Okay. So beta going to 1. And in that case, we actually know that even if particle is emitting isotropically in its rest frame, right, there is this thing called forward beaming, and most of the power actually goes in the forward direction. This we did even without the present considerations that, you know, angle is of order 1 by gamma. You recall this? This is just a consequence of an aberration. Right? We mapped this 90-degree in the lab, in the particle rest frame, to some angle which was like 1 over gamma. Recall this?
Yes, sir.
Hello? Yeah. So what we are actually saying is that most of the radiation is actually coming in a very small angle. So we can take beta going to 1 and theta, you know, almost close to 0. So this is relativistic limit, you know. And what do we get in that case? So mu equals cos theta, and this is in lab frame, is equal to 1 minus theta prime theta squared by 2. Right. So in the particle rest frame, it's isotropic. So we cannot, you know, theta prime is not close to 0. This is not true. But theta is, you know, for most of the power coming out, theta is actually close to 0. You understand the difference? In the particle rest frame, it's almost isotropic. Whereas in the lab frame, in which particle is moving close to the speed of light, most of the power comes out in the forward direction in a very small beam. Okay, so this is mu. What about beta? Beta is equal to 1 minus 1 by gamma squared. Right? You know, you recall gamma is equal to 1 by 1 minus beta squared. This is gamma squared. So we can actually write beta as 1 minus beta squared equals 1 by gamma squared. So we can actually write it like this. And gamma is much bigger than 1. So this is like 1 minus 1 by 2 gamma squared. Right? I mean, we're just doing a binomial expansion. So beta is close to 1 as gamma is much bigger than 1. So what happens in this case? So this factor gamma 4 1 minus beta mu 4 1 by that. What happens to that? That will just become, you can easily show it. This is 2 gamma by 1 plus gamma squared theta squared whole to the power of 4. Right, you can actually show it by these approximations. So the dependence of this, so dpr by d omega, right? So this is isotropic. This is the same, irrespective of omega prime, or more or less the same. So what we get is this depends on, in the case of beta going to 1, this actually depends on, it's a function of only gamma and gamma theta. So there is no as beta tends to 1. Basically, theta dependence is only through gamma times theta. Okay. So that's why, like here, we see that gamma becomes order 1 by theta becomes of order 1 by gamma. So, gamma theta is 1. So if your gamma is a factor of 10 higher, the angular spread of the forward beam will be a factor of 10 narrower. Okay. Okay, now what about angular distribution? Right, so let's consider, say, for example, so of dipole radiation as seen in lab frame. Right, so let's see. We know this dipole formula is equal to q squared a prime squared by 4 pi c cube sine squared capital theta prime. Right, this is just the formula that we derived in class for particle, for a particle with small velocity radiating, when its acceleration is a prime. So this is the, expression in particle rest frame. Okay. Now, what is this theta prime? If you recall what theta prime was, this is the angle between acceleration and n hat prime, right? This was the angle between the acceleration vector and the direction of the photon that you're considering. Okay. So let's draw a situation. So what does it become? So dp by d omega. So now we'll use this transformation, this one here, right? We're looking at the radiation. This is equal to, and we'll plug in the value for this from here. Okay, so this is equal to q squared by 4 pi c cube. What is a prime square? If you recall from the previous slide, it is gamma to the 4 a parallel squared, a perp squared plus gamma squared a parallel squared. Right, so this is your a prime squared expressed in terms of lab frame accelerations. Okay, this is this, and then we have this 1 by gamma to the 4, 1 minus beta mu to the 4, and this dpr prime by d omega prime is what we substituted. So there is this sine squared theta prime. Okay, so this gamma to the 4 goes away. So what do we have? We have q squared by 4 pi c cube gamma a parallel gamma square A parallel squared plus A perp squared by 1 minus beta mu to the 4 sine squared theta, capital theta prime. Okay, now this, what is this theta prime? So let's see, this is, say, your velocity, right? And let's say this is your acceleration in the particle rest frame, and this is some n hat, right? So all these three vectors need not lie in a plane. So this is your angle between the acceleration and the direction of the photon that you're considering. Okay. So now we will actually consider two cases. Let me actually create a little space. So we'll okay. So let me draw. The geometry. So let's see. Let's call this velocity v. This is the velocity of the particles, of a particle actually. So this is right. And we can actually, without loss of generality, we can take the acceleration to lie in this plane. So this is sort of your acceleration A prime. Okay, and this is the velocity, particle velocity. Then this is some photon direction n hat prime. So this angle is actually theta prime. So this is the angle between the particle velocity and the photon direction. And this, and so this v A prime and n hat prime do not lie in a plane. So this angle is angle capital theta. Right, so this is the angle which goes here in this expression. And so, and this angle in the xy plane is phi prime. Okay, so these theta prime and phi prime are related to this what characterizes the solid angle of the photons that we are considering. So this is the general case. Okay, but the general case is very hard to treat, so we'll do two special cases. Case one, when acceleration is parallel to the direction of motion of the the acceleration A prime is parallel to the direction of the motion of the particle. Okay, so in that case, capital theta prime is the same as small theta prime, right? Acceleration and v lie in this zx plane. Now if A prime is along v, then it's along the z-axis. So then theta prime and capital theta prime are the same. So what is sine squared? Sine squared theta prime is equal to sine squared theta prime, which is equal to 1 minus mu prime squared, right? 1 minus cos squared theta prime. So what is that? So we have that expression for mu prime here. We can actually just write 1 minus mu prime by manipulating this and remembering that beta square equals, beta is basically v by c and gamma is 1 minus beta square gamma is equal to 1 minus beta squared minus a half. If you recall that, then we can actually write this as, this is 1 minus mu prime squared can be written as 1 minus mu squared divided by gamma squared 1 minus beta mu the whole square. Okay, this is just sine squared capital theta prime. So what do we have? So what do we have? We have dp by d omega, and we can actually call it parallel because then we are considering radiation. So in the direction parallel, if acceleration is parallel to the direction of velocity, then we have this. So this is equal to, all I am doing is actually substituting in this equation the expression for sine squared theta prime. So what do I have? And of course a perp is 0, so what do we have? We have q squared by 4 pi c cube. A perp is 0, so this is gamma squared a parallel squared 1 minus beta mu to the 4, and sine squared theta prime is 1 minus mu square is nothing but sine squared theta, right? 1 minus mu square is 1 minus cos squared theta, which is sine squared theta, divided by gamma squared 1 minus beta mu whole squared. So this gamma squared, that gamma squared cancel, and this makes this 6. So this is the 6th power. Okay, so this is the expression for power when the acceleration is along the direction of the velocity of the particle. Let's see. So what is the situation that we have now? So if this is the velocity of the particle, your acceleration is also along that. So if the acceleration is along this direction, then you know that in the lab frame, in the S prime frame, this is the radiation beam, right? It is nothing comes out in the direction of acceleration. So this is V, and this V is parallel to, or acceleration is parallel to V. Acceleration is parallel to. So so in the lab frame, so this is the particle rest frame. In the lab frame, what does it look like? In the lab frame, what does it look like? And if we consider beta going to 1, particles are relativistic, then you see at theta equal to 0, you get 0 power. So there is no power at theta equal to 0, but you have these lobes. Right? So at theta equal to 0, it will give you 0. And so basically this power which was emitted in this direction, it all gets forward beamed, and it gets forward beamed on an angle in the lab frame of order 1 by gamma. You understand that? It's when theta equal to 0. So this theta is this angle, right? Theta is this angle between n hat and velocity. So okay, and we had actually done this, when we went to beta going to 1 limit, we said that power is actually a function of gamma theta, right? So the theta dependence is through gamma theta. So when theta, you will see that for theta equal to 0, you get 0, but this again is forward beamed to almost the same solid angle that we motivated last time. Let's see. So let me actually just write down. So we did this manipulation previously, right? Where we showed this, right? For the ultra relativistic limit where beta goes to 1. So this actually becomes, so for beta going to 1 limit, this becomes dp parallel r by d omega is equal to 16 by pi q squared a parallel squared divided by c cube gamma to the 10. Right, so this actually gamma to the 10 comes from this, these formulae. 1 minus beta mu to the 6 will give a very strong dependence on gamma. Gamma to the 10 gamma squared theta squared by 1 plus gamma squared theta squared to the power of 6. So this 6 is just this 6. So you see that, if you plot this as a function of theta, you will say that it is peaked, right? If you plot this guy, f gamma theta, you will see that this peaks at order unity, right? When theta is 0, this is 0. So f as a function of c, the argument, it starts at 0, peaks at z of order unity or some constant number, and at large c, at large gamma theta, this denominator starts dominating, it falls off. So this is basically the beam pattern that you're seeing. Now this is the parallel case. Second case is the perpendicular case. So A prime is perpendicular to velocity. What happens in that case? This A prime is here basically along this direction, along x direction. So what happens in this case? Let's see. Okay, so in this case, cos theta prime is equal to, what is cos theta prime in this case? This is equal to sine theta prime cos phi prime, right? So basically this is the angle, if we consider this as spherical coordinates and this is r hat, n hat is the same as r hat, this is the x direction, so this is x, y, z, right? Our spherical coordinates. So then the angle between the x hat and r hat is nothing but this. Do you see what I'm trying to say? This capital theta prime in that case is the angle between r hat and x hat, and that can easily be shown to be this angle between r hat and x hat in spherical coordinates. Okay, so what is sine squared? This is what we'll need right in our formula here. So what is that? That's 1 minus cos squared theta prime. And what is that? This is equal to 1 minus sine squared theta prime cos squared phi prime, right? Just from this above expression. And how is this given? So phi prime, so this, we want to write it in lab frame variable. So 1 minus, so sine squared theta cos squared phi, and then we did this actually here, right? So this is the expression. This is how sine squared theta prime can be written, right? So this is sine squared theta. Sorry, not so much. Yeah, this one. This is what we are after. So sine squared theta prime is sine squared theta. So this, the above thing is sine squared theta. sine square theta divided by gamma squared 1 minus beta mu whole square. Okay, so this is what we get for sine squared theta prime. So your dp perp r by d omega is equal to q squared a perp squared by 4 pi c cubed. I'm just sort of writing this formula, this one. Times, so now a parallel is 0, a perp is not 0, so 1 minus beta mu to the 4, and now the sine squared theta prime, which is 1 minus sine squared theta cos squared phi by gamma squared 1 minus beta mu whole squared. Okay, so this is your formula. Again, we can take beta going to one limit and simplify it, and you will see that this is about 4q squared a. Sorry for this. There's a lot of mathematics here. Not very hard. You have to be very careful just about these. What is meant by these various symbols? Once you are careful about that, it's just tedious. You can easily do it. Pi c cubed. So this is, so now we have to just write this 1 minus beta mu in this limit when theta is close to 0 and when beta is 1, close to 1. So this becomes gamma to the 8, 1 minus twice gamma squared theta squared cos 2 phi plus gamma 4 theta 4 divided by 1 plus gamma squared theta squared to the 6. Right, so this is what it simplifies to. And what about the geometrical picture? So now in this case, in the lab frame, right, so acceleration is along the direction of velocity, right? So this is the direction of velocity, and acceleration so acceleration is in this direction. So this is a prime and this is the direction of velocity, right? Here they were parallel, a parallel and v, a parallel prime, a prime, sorry, not a parallel, a parallel, sorry, a prime and v were along the same direction. Here a is perpendicular, a prime is perpendicular to the direction of the particle, right? So what happens in this case, you see, when theta is, when this expression is maximum when theta is 0, right? Because the denominator just becomes 1 and this negative thing goes away. So basically what this becomes is something like this. And so basically you again, there is emission at an angle of order 1 over gamma. Okay, but in this case for theta equal to 0, it's not 0 because acceleration is actually perpendicular to the direction of velocity. Okay, so you can actually see, if you make a plot of this function, again g as a function of xi, you will see that now this is not 0 at xi equal to 0. Xi is just gamma theta. It actually starts at the maximum and then decays. And this has a width of order, gamma theta is order unity at this point. Do you see the significance of these figures that I've drawn? This one and this one. More than these mathematical expressions, you have to have a feel for this, that there is no radiation along the direction of acceleration. So you will have null here. There is no radiation here. But just beyond this, you will have very high radiation coming. In this case, when acceleration is perpendicular to the direction of velocity, there is forward beaming and you have maximum at theta equal to 0. Is it clear? Is there anyone out there?
Yes, sir.
Sorry about the long class, but I just wanted to finish this material. This is like tedious maths, but the most important thing is, knowing what we are actually trying to do, right? So, this figure is important. The fact, the whole program here was actually to go from the particle frame in which we know all these expressions for Larmor formula and for the dipole formula of angular distribution, to use these Lorenz transformations for angles to go to the lab frame expression. Okay, so this was the whole program. So the individual mathematical steps are not that hard, but in the end we get something which is quite nice and useful that we can apply to applications. Okay, so this we'll actually be using somewhat when we do synchrotron emission, which is emission of emission due to relativistic particles, which are so so if you have magnetic fields like this, and if you have relativistic particles going around the magnetic field, so then you have and you're looking at various radiation along different directions. Okay, so in some cases we can consider like acceleration is towards the center, so acceleration is perpendicular to the direction of velocity. So a perp not equal to 0. This would be right. This would be, so if you have electrons going like this, so the acceleration is towards the center and velocity is perpendicular to it. So a parallel is 0 and a perp is not 0, a perp parallel prime. So we can actually apply these formulas, and we will do that actually when the time comes. Okay, so basically what you'll yes please.
In case of dipole means formula, we have a parallel in the direction of v. Means, but a
No,
perpendicular.
no. No, in case of simple dipole, that's correct, right? So if you have a simple linear dipole which is just doing this, right? Acceleration is in this direction and velocity is also in this direction. Yes, that is correct. But like you can also think of the circular motion as a generalization of dipole, right? It's like you can add this and this with a phase of 90 degrees, right? A circular motion can be thought of like two two linear polarizations but a phase difference of 90 degrees. You see what I'm trying to say? So even for particle gyrating around magnetic fields, you can think of it as independent dipoles. One dipole is sort of accelerating like this, and the other dipole is accelerating like this, and they have a phase difference of 90 degrees. Okay, at an instantaneous position, right, for this circular motion case, acceleration is actually perpendicular to the direction of velocity. So basically an observer here, which along which the particle is moving, will see a very large radiation coming towards him for a very short time. Okay, we'll actually come to this later on. So is there any other question?
So you are trying to say that A can be perpendicular to V in case of circular motion.
Yes, yes.
I can only understand this.
You can understand it or not? So
in case of circular motion, it is quite correct.
Right. So see, circular motion can be thought of two dipoles with a phase difference of 90 degrees, right? You can have right. So velocity equals v naught cos omega t x hat plus sine omega t y hat. This is circular motion, right? You can actually think of this as dipole in x and y, but with a phase difference of pi by 2. Okay. But in a circular motion, acceleration is always towards the center, so, and velocity is tangential, so they are always perpendicular. Anyway, you read the book. So in the next class, we will actually finish chapter 4 and start with the application. So till now, we were actually just building theory and theoretical ideas that we'll need later on. So we are at halfway of the course, right? Now we have built up all the tools that we need for understanding various radiation mechanisms. Okay, starting from free emission to synchrotron emission to Compton scattering and whatnot. Okay, so this is sort of like a midway in the course. So I encourage you to actually brush up stuff in the first 4 chapters, because we'll need all of this later on when we do applications. Okay. Anything else? So let me stop sharing. And we'll meet on Wednesday. I'll also stop recording. Okay, bye. Take care.